Welcome to MarkScheme, Compound Interest. Everything you need made visual. Put $1,000 in the bank at 5% a year. How long until it doubles? A tempting answer. 5% times 20 years is 100%. So 20 years. But that's wrong. And it's wrong in your favor. It's actually about 14. The reason is compounding. Each year, you earn interest on your interest. And that snowball is the whole story of this video. Here's exactly what we cover. Straight from the syllabus. Analysis and approaches. Standard level 1.4. Compound interest, both annually and for other periods, like monthly or quarterly. Annual depreciation. And using the finance solver on your graphing calculator for real-world problems. One thing we'll flag, but not finish. Solving for how many years? Because that needs logarithms, which is the very next video. Let's build the formula, not memorize it. You start with the principal, capital P. After 1 year, the bank adds R% of it. That's P plus R over 100 times P, which factorizes to P times 1 plus R over 100. So 1 year of interest is just multiplying by that bracket. Now the key idea. Year 2 multiplies by the same bracket again, so we get the bracket squared. Year 3 cubed. Each year is the previous balance times the very same number. If that feels familiar, it should. It's a geometric sequence, exactly the one from the geometric series video, with common ratio 1 plus r over 100. So after n years, the future value is p times 1 plus r over 100, all to the power n. Let's watch that snowball. 2 accounts, each starting with $1,000 at 8%. On the left, simple interest. It adds a flat $80 every year, so its bar climbs in equal steps, a straight line. On the right, compound interest, multiplying by 1.08 each year. Early on, they look almost the same. But keep going. The compound bar starts pulling ahead, and the gap between them doesn't just grow. It grows faster and faster. Because compound interest is earning interest on interest the other account never sees. After 12 years, the compound account holds about $2,500 versus $1,960 for simple. And every year after, that distance only widens. Same rate, same start. The multiplying is what does it. Banks often pay interest more than once a year, monthly, quarterly, daily. Two things change. If the yearly rate is R% split over K periods, each period earns R over K. So we divide the rate by K. And in T years, there are K times T periods. So the power becomes K times T. That gives the general formula. Future value equals present value times 1 plus r over 100k, all to the power kt. Take $1,000 at 5% for 1 year. Compounded annually, it's 1,000 times 1.05. Quarterly, each quarter earns 1.25% to the power 4, about 1,050.95. Monthly nudges it a little higher again. More frequent compounding always earns slightly more. But notice the jumps shrink. It doesn't run away to infinity. Depreciation is the same maths in reverse. A car, a phone, a laptop. Each year, it loses a percentage of its value. If it loses R%, then it keeps 100 minus R%. So you multiply by 1 minus R over 100 each year. Same geometric sequence, but now the common ratio is less than 1. So the bars shrink. Here's a car worth $18,000, losing 15% a year. Watch it decay. Each bar is 85% of the one before. It doesn't drop by the same amount every year. The losses get smaller as the value does. But it keeps falling, year after year, towards zero, without ever quite reaching it. Time to lock it in with a ladder of examples. My own numbers, exact IB style, easy to hard. Example 1, annual compounding. $2,000 at 4%, compounded once a year for 6 years. Always start by stating the formula. Future value equals present value times 1 plus r over 100 to the power n. Substitute in 2,000 times 1.04 to the 6th. Type that in one go, and you get $2,530.64. That's the whole method for annual compounding. Example 2 steps it up to monthly compounding. $1,500 at 5%, compounded monthly for 3 years. Now we need the general formula with k periods a year. The rate per month is 5% over 12, 0.05 over 12. And here's the trap that catches half the room. The power is k times t, 12 times 3, which is 36 periods, not 3. Keep every digit until the end, and it comes out to $1,742.43. Example 3 flips growth into decay. A car worth $18,000 loses 15% of its value each year for 4 years. Depreciation, so the multiplier drops below 1. If it loses 15%, it keeps 85. So the multiplier is 0.85, not 1.15. 18,000 times 0.85 to the fourth gives $9,396.11, just over half its value after 4 years. Same one idea as before, only shrinking. And if a question ever asked how many years to have, we'd need logarithms. That's the very next video. Example 4 is the one that separates the A students. Account A pays 5% compounded annually. Account B pays 4.9%, a lower rate, but compounded monthly. Which account is actually better after 1 year? You can't just compare 5 against 4.9. You have to compare what each really grows by. So compute the effective annual growth of each. Account A just multiplies by 1.05, an effective rate of exactly 5%. Account B multiplies by 1 plus 0.04, 9 over 12, all to the 12th power, which works out to about 1.05012, an effective rate of 5.012%. 5.012 beats 5. So account B wins just barely, even though its headline rate is lower. That's the power of more frequent compounding, and it's exactly the comparison exam questions hide. Turn every offer into its effective annual rate, and then it's a fair fight. Before the exam craft, one lovely shortcut that ties our whole story together. Remember the hook. How long for money to double? There's a mental trick. The rule of 72. The number of years to double is roughly 72 divided by the percentage rate. At 5%, that's 72 over 5, about 14.4 years. And there's our answer from the very start of the video. about 14. But be careful. This is only a quick approximation, a back of the envelope estimate. It is not a syllabus formula, so don't write it as you're working. The exact number of years needs to undo an exponent, and that tool is the logarithm, the very next video. Now the exam craft. First, your calculator has a finance solver, the TVM solver, and it's brilliant. But there's one trap that catches everyone: the sign convention. Money you put in, the present value, is entered as negative. Money you get back, the future value, comes out positive. If both have the same sign, you'll get an error or nonsense. Second, match the periods. Enter the interest as the yearly rate, but set the number of periods to k times t. 36, not 3, for monthly over 3 years, and set compounds per year correctly. Third, round only at the very end. If you round the multiplier early, the error compounds too. Fourth, watch the wording. Per annum means per year. A nominal rate is the yearly headline, split across periods. And since finance sits on paper too, give 3 significant figures. And fifth, to compare two offers fairly, convert each into its effective annual rate, 1 plus r over k to the k minus 1. And always read whether the interest is simple or compound before you start. 4 traps before we finish. 1. The multiplier. 5% means times 1.05, not 1.5 and not 1.005. Turn the percentage into a decimal carefully. 2. Under non-annual compounding, count periods, not years. Monthly for 3 years is 36 periods, not 3. 3. For depreciation, use 1 minus r, not 1 plus r. The value is falling, so you must multiply by less than 1. And 4. Don't round the multiplier early. Chop 0.00417 down to 0.004. And, raised to a big power, it quietly shifts your final answer. Keep full precision and round only at the end. Avoid these. And financial maths is easy marks. And that's SL 1.4, fully covered. Compound interest for any compounding period. Depreciation as a shrinking geometric sequence, and the finance solver on your GDC. The one question we kept postponing, how many years to reach a target, needs to undo an exponent, and that tool is the logarithm. That's next in the course. For more, that's markscheme.app. See you there.